Welcome to Module 1.3, Hazardous Substances, the Circular Economy, and Climate. In this section, we explore how chemical safety, resource efficiency, and climate goals are deeply interconnected.
In a circular economy, materials are kept in use for as long as possible. First, by extending their lifetime. Second, by reusing them at the end of the first service phase. Third, by finding new purposes once reuse is no longer feasible. And finally, through recycling, which in practice often means downcycling. To make these stages work, decisions made during product design and initial use are crucial. Hazardous substances complicate this process by limiting safe reuse and hindering high-value recycling.
To extend service life, many materials rely on additives such as antioxidants and anti-UV chemicals. Antioxidants protect against oxidation, while UV stabilizers prevent damage from sunlight. These additives improve durability, but some also carry hazardous properties that must be considered. For example, roofing materials often require chemical additives to prevent early degradation. Some anti-UV chemicals used in paints, coatings, sealants, and adhesives, such as hals and benzotriazoles, come with environmental and health risks. They may be toxic to aquatic life, cause irritation, or even harm the ozone layer. When we move to reuse, uncertainty increases. Chemical regulation is slow, often taking 10 years between identifying a hazard and implementing restrictions. Currently, around 240 substances are listed as substances of very high concern. A product considered legal today may be prohibited in the future if it exceeds new limits. Using chemically complex materials is effectively a gamble. Their future reuse may be blocked by evolving regulations.
Asbestos illustrates this challenge. Once widely used for its durability and fire resistance, it is now linked to severe diseases, including lung cancer and mesothelioma. Many older building elements still contain asbestos and could technically be reused, but it is now banned in new construction in many countries. This shows how past chemical choices can prevent safe reuse for decades.
In recycling, material purity is essential, but chemical additives are not removed during mechanical recycling. Different products are mixed together without detailed analysis of chemical ingredients, resulting in recyclates that contain an unknown chemical cocktail. This undermines quality and limits their usability and recyclability. Untreated solid wood is an excellent example of a material that fits circular principles well. It is a monomaterial, contains no hazardous substances, and can be easily turned into chipboard or wood fiber insulation. Pure, non-toxic materials enable high-value recycling.
In contrast, wood polymer composites are difficult to recycle. They combine multiple components that cannot be separated and often include hazardous additives. Such materials typically cannot be recycled at high value and may end up as waste or require incineration. Climate change arises from the collision of natural systems and human activity. Addressing it requires transforming not only energy systems, but also the way we produce and consume materials. Circularity plays a key role in preventing emissions, not only during use, but across the entire life cycle, from extraction to disposal.
Switching energy systems from fossil fuels to renewables addresses roughly 55% of global emissions. The remaining 45% comes from how we make and use products, materials, and buildings. A shift from a linear to a circular economy is therefore essential for reaching net zero emissions. Chemical pollution and climate change are often treated separately, but they are closely linked. Hazardous substances contribute to climate impacts, while climate change increases exposure risks. Understanding these interconnections is critical for sustainable construction policy and design. Producing toxic chemicals is energy-intensive and relies heavily on fossil fuels. Toxic materials often create more waste, generating further CO2 emissions through incineration. And designs that depend on petrochemical products lead to higher embodied emissions.
Rising temperatures accelerate the release of VOCs indoors. Increased rainfall and flooding spread PFAS, pesticides, and heavy metals. UV radiation speeds up the breakdown of plastics and coatings, releasing more chemicals. Warmer, wetter conditions also increase mold growth, prompting more use of biocides.
These dynamics reinforce each other. Toxic substances block circularity. Reduced circularity increases emissions. Climate change accelerates chemical risks, and hazardous materials raise climate impacts.
Thank you for completing Module 1.3. To explore further resources, tools, and practical guidance, visit the NonHazCity3 project under Interreg Baltic Sea region.